as you have probably figured out from the last couple of videos, this chapter really is for us to just introduce a lot of the language that we're going to use throughout all of geometry. And so that's really the primary purpose of this chapter, is just to introduce a lot of the language. But it's also, you will also begin to notice that there are some abstract concepts that will begin introducing themselves in this chapter, which we will use those concepts for the rest of geometry. So in this next section, that's section 1.3, so if you want to keep your notes in order, this is 1.3. There are a couple of concepts that we're going to go really deeply into. It's not a lot of concepts. We're really only going to go over 3 concepts in this entire section. But we're going to dive really deeply into them because I feel like the deeper you have an understanding of those concepts, the more you will understand them on the surface level. And so just be aware of that. Be ready for that in this section. This section has 2 videos. Okay, so there's this first one. There are 2 videos in this section. So just know that. The first is on the ruler postulate and the segment addition postulate, and the second one is on the Pythagorean theorem. So these notes go with the next 2 videos. And so the first part of this section, we're going to introduce our first postulate, and that's what you're seeing on the screen now. Postulate number 1 is the ruler postulate. And let's talk a little bit about what a postulate is. I mentioned it in the last video that this is part of how Euclid discovered geometry, as he made these rules, but postulates are a specific type of rules. What a postulate is, and you can put this on your definition sheet, is a postulate is a rule that is accepted without proof, sometimes known as an axiom. And I'm just going to put AKA, also known as an axiom. And so, as we talked about before, rules that have to be proved are theorems. And you can go ahead and put that on your definition sheet as well if you haven't. That postulates are, and I'm going to move this down here. Postulates are a rule that is accepted without proof, and a theorem is a rule that must be proved. So think about that for just a second. In other words, a postulate is a rule that's kind of so obvious, it makes just so much sense that we don't have to go to the length to prove it. We just kind of accept it as true. And so our first postulate is the ruler postulate. What does the ruler postulate say? The ruler postulate says that the points on a line, and you can look at your postulate sheet and read along with me if you want, but it says the points on a line can be matched 1-to-1 with real numbers. The real number that corresponds to a point is a coordinate of the point. Here's what it means. If I have a number line, I can put a point at a coordinate. I can put a point at a number, and I can understand that that point means -5. And then we have a name for that. That is a coordinate. So the coordinate of, we'll call this point A, is -5, right? So the coordinate of point A is -5. Well, let's say I have another coordinate at 5. Let's call this coordinate B. So I have A and B. A is -5 and B is 5. All the ruler postulate says is that I can basically do what I just did, that I can put points at different coordinates and that those points can represent number values. That's the ruler postulate, that points can represent number values. And we often, when we talk about a number line, we often talk about this as, think of this as an x-axis. Right, on an xy axis. This is just the x-axis. Then this point would be x1, and this, and excuse me, and this point would be x2. The first x coordinate and the second x coordinate, and these are the coordinates. So x1 and x2 are technically the coordinates. But A and B are the names of the points. So I'll write that down. And I'll do it in green, actually. A and B are the names of the points. And x1 and x2 are the actual coordinates. Okay. But we can also refer to A and B as coordinates. But most often when we're talking about just the left and right direction, we're referring to things in the x direction. So those are the x1 and x2 coordinates. And that's a subscript. This just means the first x coordinate, and this just means the second x coordinate. There is a distance between these 2 points, right? These points have a certain distance. And the distance between 2 points is written like this, AB. This refers to the distance between A and B. When I write A and B together, that refers to the distance between points A and B. And you can see that here, it's easy to figure out what AB equals. Let's just count. Let's count the number of points that they are apart from each other. So I'm going to start at -5 and I'm just going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So AB, the distance between points A and B is 10, right? So remember, this means the distance between points A and B, and we know that that is 10. So AB is 10. If I wanted to, in general, write a formula for what I just did, how would I do that? How could I figure out this for all points? Well, the formula for distance goes like this. AB, the distance between 2 points, is going to be the second coordinate, which is x2, minus the first coordinate, which is x1. Okay, and now let's do that in this case. If we subtracted 5, the second coordinate, minus -5, 5 minus -5 is, of course, 10. So that works. Okay, so the distance between these 2 points is positive 10. But distance always has to be positive. So you could see where we might have 2 negative numbers and might be adding to get a negative number here. So what we do is we say that the distance between A and B is actually the absolute value of the second coordinate from the first coordinate. And that's how we find distance, is always subtracting the second coordinate from the first coordinate and taking the absolute value. AB is also called the length of segment AB. Remember, how do we denote segment? We denote a segment like this with a little bar over it. So we could say that AB, which means the distance between points A and B, is also the length of, that's bad G, the length of segment AB, right? That there, if we drew this as a segment, that the length of that segment would be 10, and that A would be one endpoint and B would be another endpoint. So that's the ruler postulate. Basically says that we can put points at different values, and if we needed to, we could use this formula to find the distance between these 2 points. So let's move on to postulate number 2. Postulate number 2 is the segment addition postulate. If you remember, we talked last time about collinear points, and I'll actually write that out real quick. I had you put on your definition sheet what collinear points means, and collinear points are just 3 or more points on the same line. So if I had 3 collinear points here, so here's a segment right here, and let's say I had 3 points, and I'm going to draw those points on here. There's one right here. I'm going to call that point A. There's another one, let's say I drew another one right here. That is B. And there's another point over here, which is C. Okay? Then what we say is that if there are 3 or more points on a line, then there has to be 1 point or more that is between 2 other points, right? That if I have 3 points on a line, and they're all on the same line, then there is no way that I cannot have 1 point in between the others. And obviously, we say B here is between A and C. So the language we would use is B is between, point B is between A and C, and there's no way for that to happen. There's no way for that not to happen if there are collinear points. But we can also do some math with this. So then we say the segment addition postulate says this, says if B is between A and C, then, and then I'm going to write out what's rest, then we say AB plus BC equals AC. And let's take a second and really examine what all of this means. Okay, remember when we write AB right here, what that means is the distance between A and B. The distance between A and B. And so the distance between A and B plus the distance between B and C equals the distance between A and C. If we were to draw this as a picture, look at it up here. This distance, which we call AB, plus this distance, which we call BC, equals the entire line segment, which we will call AC. And once again, you should be saying, well, duh, and that's why this is a postulate, because it doesn't need to be proven. I can just take a look at one segment and see that this is true. And this rule, the segment addition postulate, actually comes in handy a lot. It comes in handy a lot in math. And that's all that it is, that if I have 3 points on a line, then the 2 segments that are created by this point being here, this point B, A, B, and BC, when I add them together, I get the entire segment, which is AC. That is the segment addition postulate, and that's it. It's that easy. So what can we do with that? Well, let's do an example, and then we'll be done with the first part of this video. So if y is between x and z, now right away, as soon as you see that, a picture should come to your mind. You should be thinking, okay, if y is between x and z, then I have a line. X and z are clearly the endpoints, and I have a point in between them, which is y. This is what this first statement looks like. This statement, if y is between x and z, has a picture attached to it, and that picture is this. As soon as you see things in geometry that have statements like this, you should automatically be thinking of pictures in your head. So if y is between x and z, then what is true? Well, here's what it's saying is true. X, y, this distance right here, is 2m plus 3. So we don't know its length, but we know it can be represented with this expression. Yz is 3m minus 8. And xz, which is this whole distance, is 20. And it tells us to find m. Well, how can we find n? Well, we're going to use the segment addition postulate to set up an equation that we know is true and then solve. What do we know is true? Well, by the segment addition postulate, we know that xy plus yz is xz. That this segment right here, xy, the distance between x and y, plus the distance between y and z equals the entire distance between x and z. Well, we can represent these in different ways. For example, xy is 2m plus 3. Yz, I'm adding, this comes down, is 3m minus 8. So where there's a yz, I can just replace it with 3m minus 8. And xz is 20. This is an expression that I can now solve. And so I'm going to do that. 2m plus 3m is 5m. Positive 3 minus 8 is negative 5 equals 20. Now I need to add this 5 over to this side, so I'm going to come over here and finish my work. If I add 5 to both sides, then those cross out, and what I have left on this side is 5m, and then 20 plus 5 is on the other side, which is 25. And then to get m by itself, I need to divide both sides by 5 because these are connected by multiplication. And m is 5. So that's an example of why we would use the segment addition postulate to help us find different values. And then I could go back and I could even find exactly what the distance between x and y and z would be if I went back and plugged in m. But that's how we use the segment addition postulate. So what if I asked you, are x, y, and yz congruent segments? Well, what does it mean for segments to be congruent? Well, what it means is that their lengths are the same. So here, congruent segments, what does that mean? It means their lengths are the same. So if I asked you, are xy and yz congruent segments, what we would do is we would go back in, plug in 5 to see if we get the same thing. So let's do that. Let's plug in 5 into here, into 2m plus 3. 2 times 5 plus 3. 2 times 5 is 10, plus 3 is 13. 3m minus 8. 3 times 5 minus 8. 3 times 5 is 15. 15 minus 8 is 7. So these are not congruent. And the symbol for congruence looks like this. The symbol for congruence is an equal sign with a little squiggly over the top of it. If they were congruent, we would write xy, segment xy, is congruent to segment yz, which means the same thing as, and I really want you to understand this, this means the same thing as the lengths xy and yz are the same. These mean the same thing and they're just written differently. If the segments are congruent, this congruence refers to more of the geometric qualities. If the segments are congruent, then that means the lengths or the distances between these 2 points will be the same. So this is the same way of writing two different things. But in this case, that is not true. xy is not congruent to yz, and xy is not. The length of xy is not congruent to, is not the same as the length of yz. So that is the first half of this section, the ruler postulate and the segment addition postulate. What I want you to do is I actually have a set of practice problems specific to this first half of this section. I want you to go ahead and do those first before moving on and watching the next video.